Okay, I'm going to use this example that we just did to talk about a completely different way of expressing a vector. Okay, so when we first started, if we run through real quick everything that we've seen thus far, and I don't have videos on all this stuff, but if you've been in class and paying attention, keeping track of the notes, then you should have this. We've talked about how a vector can be expressed as 2 points, one of them being the initial point, one of them being the terminal point. But the whole purpose of having those points is to calculate these components so that we can write the vector in component form, right? So component form was essentially the first format we learned about for writing the physical characteristics of the vector, all right? We talked about this being the run and this being the rise. And then we did some work with that to find magnitude and direction angle. Then we spent a little bit of time talking about the second format for this, which was linear combination. We said the linear combination of a vector basically represents the vector as a sum of two other vectors, right? That not as much a big deal as understanding how we write that. So if you have the components of the vector, all you have to do is take the horizontal component and slap one of these bold-faced I's after it. That still represents the horizontal component or the run, and then the second component gets a J after it. So this is the second format that we learned to express a vector. Those are good, and there's another video coming up on how, those are good if you want to know the physical components of run and rise. How far horizontally, how far vertically does the vector represent? Now, I'm going to use this example that we just did to come up with a new format for this, okay? And it's all based on right triangle trig with some substitution. So I'm going to take this triangle, okay? So this distance here, it's not quite perfect. I tried to match it up. Represents the -5 horizontal component and the -7 vertical component for this vector. I'm going to take that. We calculated the magnitude for this as radical 74. Okay, and I don't want to break any mathematical canon here, but I may mess around with that a little bit. Okay, so here's this. Let's label everything that we just saw with that. This was -5. This was -7. Over here we got the square root of 74, and then we actually calculated this as 54.5 degrees, okay? Even though you recall, if you watched this previous video, it's actually 234.5. I'm going to come back to that in a second, all right? Now, the component form of this vector v is -5, -7, okay? However, when you start looking at application problems, word problems, right? Knowing how far something moves left and right is not nearly as important or not nearly as useful as knowing its magnitude and its direction right off the bat. That's why we've been spending so much time calculating those. That's really what's important to know about a vector. We're going to talk about that more when we talk about velocity and resultant force, okay? That's coming up. So what we need is a better format. We need a more useful format for these vectors than just the run and the rise. Okay, so I'm going to use this example to kind of piece that together. Okay, the magnitude we have over here is radical 74, which is great. Now, when you look at this, we're going to take the stance of right triangle trigonometry and try to extrapolate this new format for the vector. If I want to express this distance right here, okay, if I want to express that distance, that's -radical 5. How can, and this is where it gets a little crazy, how can I express this distance, but do that in terms of its magnitude and the angle? So I want to be able to express this distance right here, but I want to use this number, and I want to use this number. Okay, so again, how do I relate this to this and this? These two sides and this angle, is there any relationship you've ever learned about in your entire math career with a right triangle where you know an angle and you know two sides, you could set up some kind of relationship, okay? I'll pause. Hopefully, you were thinking about cosine, okay? Because the cosine of this angle is equal to the adjacent side over the hypotenuse. If we write that relationship out, cosine of 54.5 equals the adjacent side over the magnitude. Oh! Hello.
Hello.
It's learning time.
Good morning,
And there's
everyone.
Mr. Markey right on cue.
Just a reminder that we
Come on in.
have free breakfast from Panera and coffee in the cafeteria. So anyone in the building working right now, please
Click.
stop on down to the cafeteria. If you can't,
Free breakfast!
let us know and we can bring you a sandwich. Just let any of our administration know, or
Come on
chat,
in.
or
Come on
email
in.
any of us. We'll try to bring you down something if you can't leave your office.
We're not
And
scared. We
also
ain't
will
afraid of
have
no
lunch
virus.
today.
No,
So
we ain't
bring it on.
We ain't afraid of no
breakfast
virus.
is available right now.
Just
in
making
the
your
cafeteria,
YouTube
and
channel
lunch
debut.
will be available
Thank
later
you.
on this morning.
You're
We'll
welcome.
remind everyone about what time. Thank you.
I don't know how to do this. Jackson's
Well,
a little better with technology than I am.
This is called a video camcorder. They've been around for like 4
I know, but I don't
years.
know how to upload what I do to
Oh,
Squealer.
I got you.
I could do this, but
Yeah.
I don't have a video camcorder.
Okay, you want to borrow mine?
No.
Okay,
I'm gonna do mine on my smart board.
okay.
But so they can actually see you as well.
Yeah, man.
That's good.
Why, I mean, wouldn't you want to?
Well, I'm seeing you in live and in the flesh.
Just
It's
saying,
better.
right? Free coffee, free breakfast.
Yeah, wow.
All right.
All right, man.
Okay, I'll see you around.
Yeah, maybe, I
You
don't
ain't
know.
afraid of no virus? What?
Maybe that's the way to go. I don't know.
I got stuff. I'll come over. I'll show you. I got something for you. All right. So anyway, hopefully you enjoyed that. Here we go. So this relationship right here represents the cosine of the angle in terms of these two sides. Now what I said from the beginning is, if you want to express just this number in terms of this angle and that number, if we multiply both sides here by radical 74, I realize this is getting a little weird, then this expression, radical 74 times the cosine of 54.5 is equal to -5. If you can follow along, what we've just done is we've expressed this number right here like that. Okay, so we can express the horizontal component of the vector in terms of the magnitude and the angle, and again, this should really be that 234.5, but you get the idea, you're going to get the same value here. So we can put this in place of that, all right? And if I went through the same process again, and if that makes sense, that's awesome, okay? If I went through this exact same process again and tried to do this for -7, this angle and the magnitude, we wouldn't be using a cosine function to represent that. We would be using since this is the opposite side from that angle and this is the hypotenuse, we would be doing the same exact thing, only we would have sine instead of cosine. So this expression would be the exact same thing, but instead of cosine, it would be in terms of sine. So again, we have expressed this number in terms of the magnitude and direction angle, and I can put this here. A full replacement of those values. So, long story short, which, if I haven't expressed it at this point, there's a song called Long Story Short by the Avett Brothers. And every time I say long story short, which I happen to say a lot nowadays, you should pause this video, go listen to that song, because it's tremendous, okay? Long story short by the Avett Brothers, check it out. Now that we have these numbers representing these numbers, I can change the way that I represent the vector's components. I can say that it's the square root of 74 times the cosine. Now is when I'm going to make that switch. I realize I've been using this but it's because I had to use that for the right triangle for the, to do the trigonometry. This is actually the direction angle of the vector, right? If you saw the previous video, then you remember that. 234.5, that's what I have to put here. The actual direction angle of the vector, the magnitude, okay, of the vector. And then this is in place of just that number -5, and then in place of the number -7, which was the second component, I'm going to put this. Okay, so, long-winded answer. You can write the component form of a vector as so, if you know its physical run and rise. New format, if you know the magnitude and the direction of the vector, you can write it like this, using cosine for the horizontal component and sine for the vertical component, which tells a better story. We're going to see that as we progress through some of these videos, as we start talking about word problems, real world applications. Okay?